One ordinary evening, Arjun found himself wondering about a question that would change the way he saw the world.
The more he searched for answers, the more he realized that some problems seemed impossible for even the most powerful computers.
Determined to understand more, Arjun headed to the university library, hoping that somewhere among thousands of books, he would find a clue. As he turned the pages, one phrase captured his attention: quantum computing. How do scientists actually visualize what is happening inside a qubit? The answer lies in a powerful geometric representation. This is the Bloch sphere, a powerful way to represent the state of a single qubit in three-dimensional space. The Bloch sphere is a geometric representation of a two-level quantum mechanical system. Here, the North Pole represents the pure state 0. In the Bloch sphere, this represents the ground state, the absolute position of 0 probability. The Bloch sphere is a geometric representation of a qubit. Every point on its surface is a unique quantum state, where pure probability flows like water. To describe a qubit, scientists use a state vector, an arrow that points from the center of the Bloch sphere to a specific quantum state. The direction of this state vector completely defines the qubit's quantum state. Even a small rotation creates a different state. These changes are performed using quantum gates. Gates such as X, Y, and Z rotate the state vector, allowing quantum computers to process information. With tools like the Bloch sphere, scientists can design and understand quantum algorithms that solve problems beyond the reach of many classical computers. Quantum computing could transform fields such as medicine, materials science, artificial intelligence, and many other areas that shape our future.
We explored how a qubit can exist in many different quantum states. But what happens when two qubits become connected? At first glance, these qubits appear completely independent. Each seems to possess its own quantum state, evolving and behaving as a separate system. But in the quantum world, particles can sometimes form a connection far deeper than anything we encounter in everyday life. Imagine that whenever something happens to one particle, another particle displays a perfectly related behavior. No matter how surprising it may seem, their properties appear deeply connected. Suppose you place one mysterious box on Earth and another on the Moon. Somehow, they continue behaving as though they are part of the same system. When one box is opened and its result is revealed, the distant box is found to contain a perfectly related outcome. The correlation appears instantly despite the enormous distance between them. While our box analogy is imaginary, but the underlying idea is real. Quantum physics allows particles to form an extraordinary connection known as quantum entanglement. In an entangled system, the qubits lose their individual identities. Their properties become woven together into a single quantum state that describes the system as a whole. When qubits are independent, be described on its own. When qubits become entangled, inseparable, requiring a single quantum description for the entire system. Visual intuition can only take us so far. To understand its true nature, we need a mathematical description that captures the behavior of the entire quantum system. One of the most important entangled states in quantum computing is called a Bell state. This equation describes two qubits that share a single quantum state. Within this entangled state, two possibilities coexist. The qubits can both be 0, or they can both be 1, while remaining part of the same quantum system. But before measurement, the system cannot be described as only one possibility. Both possibilities contribute to the shared quantum state. So far, the qubits have existed as a shared quantum state. But what happens when we finally perform a measurement on one of them? The moment one qubit is measured, the shared quantum state changes. The uncertainty of the entangled system is replaced by a definite outcome. When the entangled qubits are measured, their outcomes are perfectly correlated. If one is found to be 0, the other is also 0. If one is found to be 1, the other is 1 as well. When the experiment is repeated again and again, the same pattern continues to appear. The outcomes remain perfectly correlated, revealing a connection far beyond ordinary chance. These results were so surprising that they challenged some of the greatest minds in physics. Even the pioneers of quantum theory struggled to understand their implications. Albert Einstein found the phenomenon deeply puzzling. He famously described entanglement as action at a distance, reflecting his discomfort with its seemingly mysterious behavior. Yet decades of increasingly precise experiments have confirmed the reality of quantum entanglement. Once seemed impossible is now recognized as one of the fundamental features of our universe. A common analogy uses a pair of gloves. If you open one box and find a left-hand glove, you instantly know the other box contains the right-hand glove. But this is not true entanglement. The gloves already had definite identities before the boxes were opened. In an entangled system, the outcomes are not simply hidden in advance. The quantum state itself determines the correlations. Imagine two dancers performing perfectly synchronized movements while separated by great distances. Entanglement can appear just as extraordinary. Today, scientists are exploring entanglement as a key building block of future quantum communication networks, enabling new ways to share and protect information. A future quantum internet may connect distant locations through shared quantum states, allowing quantum information to be exchanged in ways impossible for today's networks. Inside quantum computers, entanglement allows many qubits to operate as a single coordinated system, enabling computational capabilities far beyond those of individual qubits. Entanglement, it is just part of the story, connects qubits through a shared quantum state. But when quantum waves interact with one another, an even more powerful phenomenon emerges: quantum interference.